Yes, sir.
I think it's live now.
Yes, sir, it's live. You can go ahead.
Okay. So good evening and welcome to all the participants on this webinar. Definitely, we were expecting many more of you to be there, but that's fine. Today, we have a webinar on the electro-optic and infrared payloads for UAVs, which will be delivered by Dr. Tanvi Prakash, who is working in Larsen and Toubro in Powai. And she's also a member of the executive committee of the design division of the Aero Society of India. And plus, she is very actively involved in the problem statement creation for this year's NACDeC IX competition. So over to you, Tanvi. You can go ahead. I'll go on mute and I'll put my video also off.
Okay, sir. Thank you. Today's talk is on the topic of electro-optic and infrared cameras for UAV. As this was one of the topics that students expressed interest in to know more about. The aircraft that you are designing as part of the NACDeC competition also has a similar camera on board. So it's actually going to be something which is maybe directly useful to you also. So the topic was selected based on this. I'm about to share my screen. Prachi, can you please confirm once you are able to see the presentation? I'm just putting it in presentation
Yes,
mode.
ma'am.
Just confirm that you can see it
Yeah,
in
I can.
presentation mode.
Yes, ma'am, we can see that.
Okay. Okay, great. All right. Is it still okay? I just changed something from my side. Is it still okay? Okay.
No, right now it's not. Right now it's a blank screen saying
Blank
switch to
screen.
gallery view.
Oh, okay. Let me fix that. How
You have to
about
move
now?
it. Now it's coming.
Okay, okay. All right. What we are going to address today is basically what kind of cameras are there, what are the purposes for these cameras, different types of cameras, and some fundamentals covering how these cameras really work and how the data that comes from the camera is utilized. A little bit about the design of the camera itself, some electronics, some mechanical details about what goes into the camera, and then a small section about how this data is actually used by UAVs, what is the chain that this goes through towards processing of the information so that it can be useful to the end user of the camera. And of course, because this is with respect to the NACDeC design competition, there's a small section at the end which is about the impact on aircraft design and how you can go about camera selection when you're designing a UAV. The first question actually is, why do we design UAVs? The fact is, any flying object, any flying vehicle is designed for a payload. This item has paid its way on board the aircraft. So it's all called a payload. You pay for a ticket on board this aircraft. Now, what is this payload is actually the crux of why the UAV exists in the first place. If it's a camera, if it's a radar, if it's some other kind of payload like a agricultural spray payload, it has a particular mission that needs to be finally addressed for improving some process or improving someone's life. Some particular mission exists. So once you know the mission, then you can select a payload, and based on what payload you require, that's when you end up deciding what kind of a UAV platform should carry this payload. So typically, when you have a need for eyes in the sky, that time you pick a camera payload, right? Optical sensors can do all these different kinds of tasks. You will hear these tasks as payload goals: surveillance, reconnaissance, identify, detect, recognize, differentiate, change detection. For example, if you want to know whether a field has changed and how the crop is progressing with time, that's change detection. So a camera can give you all these kinds of information. It can also help you, by the way, it can also help you navigate. It can help you look at weather ahead of you. And it can also provide you geolocations by identifying land features and giving you coordinates. So there are so many ways in which the optical data coming from a camera can be used. Now, how does this actually happen? How do cameras really work? And now this is basically going to take you back to your physics from school, where we talk about photoelectric effect and all these things. Basically, what happens is you have a sensor, which is basically a material. When light falls on this, electrons are excited and current, electrons flow, so current is generated, a voltage is generated, and that electrical signal is picked up by a processor. Now, all cameras, or I should say most cameras, including the ones that are on your mobile phone, they all have a few extra features beyond just this sensor. You have so many other systems that are required to be able to make sense of of the light that's falling on it. For example, you may want a lens. You may need to focus on an object. You may want to have a shutter before that, because if you just keep bombarding the sensor with light all the time, you may not be able to capture a photograph. So what the shutter basically does is, when you click the camera button, when you take a picture on your phone, what it actually does is there's a shutter which opens and closes. Even if you're taking a video, so I'll come to this. So the shutter will basically open for some time and then shut again. So all the light that comes through the lens and through the shutter and onto the sensor is only for the period that the shutter opens. So you sometimes this word is also expressed in terms of things like exposure or exposure time. So the period that the shutter opens, that's this. And of course, the lens, it has certain terminologies associated with it, like focal length and chromatic aberrations, all these things. Now, when the sensor, as far as the sensor is concerned, let's dive a little deeper into what really is this sensor. The sensor is nothing but a set of pixels. You'll hear this word a lot. We talk about high definition, we talk about 1280 megapixels. Your 1280 pixels, you have a 10 megapixel camera, 200 megapixel camera, whatnot. So these pixels are basically little sensors which are arranged along this chip. Okay, now imagine that sensor looks like a chip. It's actually a chip. Now, if you look at the image A, this is what it actually looks like. And this image A, if I tell you that it contains 1 million pixels, you can count. You can see that, you can see that this thing is made up of 10 squares of this size. Can you make out? So 10 by 10, there are 100 of them. Now, if I zoom in on any one of these squares, it becomes like the picture B, which itself has got 10 by 10 inside it. So 100 into 100. That's 10 raised to 4. And then the one of these elements in this B contains all these pixels. So these in image C, what you see, these would be the actual pixels. So you will have, let's say again, you have 10 and then 10. So that's how you have another 100. So now it's 10 raised to 6. This is how you have 1 million pixels within this one image that you're seeing on your screen right now. So now imagine that these physical pixels actually exist, and each pixel is a sensor that picks up light from it and then sends an electric current that corresponds to the kind of light that has fallen on it. So let's say in the optical range, it's, I'll come to that. There are different frequencies for light as well. So each pixel has sent its own signal back home to the processor saying that I saw this intensity and this wavelength of light. Now all these pixels data is collected and all of this becomes basically an image. I've taken an example. This is a popular logo that you all might have seen. If you look at this logo, it's a square logo. And let's say it fits in the pixel in this way. So if you look at this B pixel, zoomed in, it looks like this. And if you just look at the corner of this, it becomes the C pixel, which now contains 10 pixels inside it. So I hope you can get a scale of how much you have to, how many pixels go into an image, okay? So when you hear terms like 1024 cross 768, you'll see terms like this. That actually means how many pixels you have in the X direction and how many pixels in the Z direction. Now, each pixel sends its own signal, like I said. And all these pixels are put together to form a whole image, right? So these are basics of computer vision. Actually, we're getting into computer vision domain now. And at the end of it, how does this data become useful, right? For a UAV. Of course, on your phone, we all are photographers in our own right. We take photos on our phone all the time. But for a UAV, what does it really mean? Let's say this UAV, for example, is a UAV like the Thar UAV, which you have to design for the NACDeC. This UAV is designed to locate a person who might have infiltrated into friendly territory against a desert background. So how do you actually go about doing this? What is the math behind it? What is the science behind it, right? So here is one important scientific principle in computer vision, which is known as the Johnson's criteria. Johnson's criteria is actually a way of defining how many pixels are required to detect, recognize, and identify a target. So now I want to stop and talk about a little about these three terms. You will hear this a lot. DRI, detection, recognition, and identification. What it actually means is detection matlab kuch to hai, something is there. That means against a desert background, if everything looks like sand, there's something there. Recognition, what is that thing? Is it a tree? Is it an animal? No, it's a human, it's a person. Identification means it is this person. It is Tanvi, or it's a soldier, or it's a, I don't know, it's a civilian or something like this. So what Johnson's criteria actually lays out is that there is a number of pixels that you need to have to be able to identify, detect, and recognize. So what it looks like is this. If you just focus on the human row first, okay, the first row, the detection criteria is 3.6 pixels upwards by 1 pixel here. What this means, the moment you see this kind of an image against, let's say the background is black, the moment you see this, you are like, there could be a human here. Oops. At this stage, once you have 13 in the vertical direction and 5 in this direction, that means 65 pixels in all, you know by this point that it's a human and it's not something else. When you start looking at identification, when you want to know which human it is, that's when you start needing more pixels. So the minimum number of pixels you require to be able to identify that there's a human in there is 28 by 8 pixels in this direction and 8 pixels in this direction. That's what the criteria says. So that's a total of around 250 pixels. So now you're getting a feel of, let's say you have a camera which has 1000 by 700 pixels approximately. You have 700,000 pixels. And now out of this, you need to identify a person. For that, you need only 250 of those pixels. So this actually determines how sensitive your camera is in a way. The same goes for vehicle. You can look at the numbers. The numbers, of course, are larger for a vehicle because, of course, a vehicle is bigger than a human. So you will find that because the vehicle is larger, you need fewer pixels actually to be able to identify. So you will see that at 2.8 by 1 pixels, you can detect. You can recognize that it's the same 13 by 5, and then 28. So you can see the way the granularity of the image is also increasing as you go from D to R to I. At D, you just know that there's something over there which looks like a truck. At recognition, you know that definitely it's a truck and not a human now. And at identification, you know which truck it is. You can say it's Ashok Leland or something, for example. So this is the Johnson's criteria, and computer vision scientists basically use this to design the algorithms that go on board the payload or on board the UAV to be able to detect, recognize, and identify activity from the air. Now, coming a little back to the science part of it, if you look at, so this is the electromagnetic spectrum, and on the top of the scale, you can see frequencies, and on the bottom, you can see wavelengths. So let's say we speak in terms of frequencies for the visible spectrum. So you'll find that you have the colors of the spectrum here, V, I, B, G, Y, O, R. So it's like the Vibgyor spectrum. And it starts at around 380 into 10 raised to 12, and then it reduces from there. So you can get a feel that the electro-optic spectrum is really small now. And beyond this, you have a much larger spectrum, which is the infrared spectrum. And the good news is that cameras can sense the infrared spectrum. The moment you get into spectrums like the microwave and the FM and the radio and the AM and the long range radio waves, you're going to need very different kinds of sensors to be able to sense this. And then when you come to the ultraviolet and the X-ray and the gamma rays, again, you need very different kinds of sensors. So the cameras, which we see most of the time, are trying to harness this part of the spectrum, the electro-optic and the infrared. Sometimes you will find some types of UAVs also have other different spectra on them, like for example UV or some other kinds of spectra, because you'll hear multispectral payloads. Now, what these payloads are basically doing is they are trying to garner as much information as possible from the target. How, for example, water behaves in a particular way when UV rays fall on it. The kind of reflection is very different. So if you want to detect water, let's say on the moon or on Mars, you send a camera which can detect that particular kind of reflection. And if you sense that frequency coming back, then good news, you have water, right? The same thing, the same concept is also used in agriculture or on remote sensing payloads in satellites, where they want to know the health of a plant. If you, for example, want to know if a particular crop has dried out because of some disease, then the water content goes down, so it looks different. So by sensing the way these different frequencies are reflected off surfaces, you can tell what's in it. And the more frequencies you can sense, the more detailed your information becomes. It so happens that for most UAV applications, the electro-optic and IR spectrum do the job without being way too expensive. Within the infrared also, there are several ranges, just like how we have the Vibgyor spectrum, the rainbow spectrum. In the electro-optic range, we also have ranges within the infrared, which are called the short wave infrared, medium wave infrared, and the long wave infrared. So now these are also kind of, in a way, different intensities that are around us. If I give you an example about infrared, let's say. So infrared this is what a picture will look like. So the picture on the right is a night camera. What it basically does is it takes visible frequencies and it increases the what do you say, the intensity, relative intensity of these frequencies, and fixes it up. And sorry. Yeah. So yes. So the infrared frequencies on the on the left side, what you see, you can see it's now a heat map in a way, because infrared frequencies are they correspond to the way heat is transmitted in the infrared spectrum. So you can see in the picture on the left, you can see that the engine part of the car is hot. So it looks a particular way. But whereas inside the car, there's air conditioning. So that looks very different because the temperature is different. Let's say for human comfort, there's 21 degrees that's been maintained inside. And the engine is really hot. It's running hot at like, I don't know, 80, 90 degrees. So this kind of information, we don't see with our eyes. We can't sense with a daylight or a visible spectrum camera. This kind of information can only come from an infrared camera. So what this essentially means is that now if I have a UAV, which can sense whether the car has an AC on or whether the engine is running or not, can tell me how long the car has been waiting. Is the car running? Has it parked in front of a building? Has it been parked there for 4 hours or has it just arrived? Now you're looking at what I'm hinting at. It can tell you important intelligence information. It can tell you much more than what just a daylight camera can tell you. There are ways to fuse the data from a daylight camera and an infrared camera. So various sensor fusion kind of packages are available these days, which help you make even more sense of the data from UAVs. The same goes also for multispectral cameras. In the case of multispectral cameras, like I said, in the agricultural field, for example, or also in the weather monitoring and weather sensing field, being able to sense the amount of water vapor in the air that's there can tell you when the monsoon is going to arrive, for example. So these kind of satellite radars and cameras are used by the Indian Met Department and the Agriculture Department to be able to make predictions for civilian purposes. Now, I thought it'll be interesting to show you how a desert looks because your problem statement is about deserts. So what you see on the right is basically the day camera or the starlight vision camera, which is like a good contrast camera. And then on the left, you have how it actually looks on the thermal camera. So we don't see this with our naked eye. Actually, this is not how it looks. The contrast has been set in such a way that it can be perceived by us. Actually, infrared radiation is all around us, but that's a different story. So you can see the kind of information that gets augmented when you have a camera that has both in it. Just imagine if you could have both, right? Infrared as well as electro-optics. So that's the reason why most UAVs, at least in the surveillance or the surveying kind of applications, have both infrared and electro-optic. Now this is okay. This is all about still photos and one frame at a time. The shutter opened once and a photo came, and then that's what you're analyzing. But what in the case of videos? What happens for videos? Videos are actually nothing but multiple images played in a short time. I don't know if you all know what this concept is. This is the concept of a flip book. This is how animation actually began in the first place. In the olden days and even now, animation is made frame by frame. You will hear this frame by frame word in cinema a lot. So what they actually mean is they will paint individually all of these frames and then they will play them in quick succession together. Previously, this used to be done using cinema reels. So the reel basically had, if you are watching a Shah Rukh Khan movie and Shah Rukh Khan is just turning his face to look left, he will be having so many shots in between, one like this, one like this, one like this, one like this, and then Shah Rukh Khan turns left to look at Kajol. So this is actually the way videos are made, by taking multiple small photographs at very small intervals. Now, how small is that interval, right? It so happens that the scientific principle behind it is called persistence of vision. The human eye is also a camera in a sense. It's also sensing data at some rate. And the rate that makes sense for humans has been decided upon. And if you have this many rate of images appearing per second, then it looks like continuous motion to you. It's a human perception thing. It's like how good your eyes actually are. So I found a nice example. So this is a flipbook animation at frames per second 2. There are 2 frames per second. So you can see that there is a person singing and then going backwards and then ends up on top of a tower. But you can make out, right? It's very like it's touchy, like it's jerky. But the moment you make the same thing in FPS 8 frames per second, now you can make sense that this person was already standing on top of a tower, and then you're zooming out the shot to look at the tower, the whole tower. So this this is basically the effect of frames per second. And a lot of the shooting that we do on our home, like mobile cameras, these are 30 frames per second. And if you have high speed cameras, 30 and 60 also is there in phones nowadays, but high speed cameras, which are used for scientific purposes like crash detection or, explosion shooting, they may be at 10,000 frames per second, because that's the event itself is very short and you want a lot of data in a very short time. So this is the impact of frame rate or frames per second. All cameras will show this as one of their specs, like how fast, how many images per second can be captured. There's another feature that cameras come in, and this again comes from the movie world, from the cinema industry. This is like a typical, film camera that is there. And there are these words called pan tilt. You'll hear these words in UAVs. So these are the two directions, the two axes about which pan and tilt takes place. Panning happens about the vertical axis of the camera. So it's left to right pan. And tilt happens about this horizontal axis, which is up and down. Now, in a UAV, you're flying above the surface of the earth. Most of the time, you're going to be looking down. Sometimes, for certain applications, you may also be looking ahead if it's an air-to-air combat scenario or some air-to-air refueling, something like that. But most of the time, you are actually operating looking down. So most of these UAV cameras come with the feature of being able to tilt from 0 to 90 degrees. So looking straight ahead and then down. And then 360 degrees about that. So what this basically does is it gives you a full hemisphere of view below the UAV towards the ground. This is the concept of the pan tilt. A lot of you would have seen these on even small commercially used drones, which are used for shooting in weddings, etc. these days. So they have these features. And the advantage of having a camera on a UAV is that the UAV itself is also a pan tilt platform. So the dynamics become very interesting, and you can get very interesting kind of shots because of this. Now, when, of course, you're in the air and you're flying, and now you're trying to capture an image, the atmosphere is not static. There are winds, there are disturbances, optical disturbances in the atmosphere, so many things. So there is reason why the image might get a little jerky, or it might start skipping. Your video might start skipping. So then what you need to do is you need to isolate the camera from the platform movements. If the platform movements are too jerky, and this especially happens in the case of smaller UAVs, when the aircraft is large, stable, steady, doesn't pan tilt too much by itself, the camera is able to stabilize, because the weight of the aircraft, the inertia of the aircraft is so large compared to the camera. But in the case of these really small drones like quadcopters, the camera itself is comparable to the weight of the entire aircraft. Let's say it's a 5 kg aircraft, you'll have a 2 kg camera on it. So in this scenario, you need some kind of stabilization for the image. And for that, what you see here is known as a gimbal. And this gimbal actually is the gray casing and the holding mechanism of this camera. You'll see that it's also got some axis, and this gimbal also stabilizes the camera. So it understands, it's looking in this image, you can see it's looking at the horizon. So let's say it's looking at the horizon, it's seeing a flat horizontal line, and now the aircraft is in wind, it's it's in turbulence and pitching, rolling, yawing, but the horizon needs to be maintained as it is. So the image, basically the image processor will send a signal to the gimbal that, oh, you have rolled by 20 degrees, so just tell the gimbal to roll back by 20 degrees. So this way it will maintain horizontality at all times. So this is an image processing feedback loop which is inbuilt into the gimbal. And now today, most cameras on UAVs come with this because, of course, there is a weight penalty that goes with it. But that weight penalty is very much justified because then your image becomes usable. It's not there in some very small cameras, like you look at the FPV camera range. Some of them don't come with image stabilization, but there is some form of digital image stabilization. Without physical stabilization, it's possible to also digitally stabilize. So it depends on the application and how much weight you're willing to add on the aircraft. And also cost, I think. It's also an expensive affair to build this. Other elements that can also be there on cameras, these are now add-ons, okay? It's not there on all cameras. My background is largely for designing UAVs for military applications. In this case, this laser rangefinders and laser designator, this becomes an important part of the camera to be able to function and give you some good information. So one of the things on the left, the thing that you see is the laser rangefinder. Basically, it sends a laser pulse and senses the distance of this of the target back to you. So it can tell you that the person on the ground, in the case of the Thar UAV, the person on the ground is at a distance of 2 kilometers from me right now. So this information can be had from the laser rangefinder. And the laser rangefinders, because it's based on laser pulses, are also fairly accurate. You can also estimate distances in different other ways, but this one is a particularly accurate way of doing it. Now, laser designators, this is something which is actually more in the weapons domain. When a UAV is used to paint a target, what's known as painting a target. So this laser beam has a kind of key on it, an encrypted key on it, and that keyed laser is projected onto a target and it's painted for another article or for another weapon of destruction to come and hit this target. So some payloads also require this kind of a use. So an electro-optic, infrared, LRF, laser designator, what else could be there? So of course, there are certain very specialized cameras which exist. They are specifically for shooting for films. A lot of shots, drone shots, have made it to movies now. If you're a fan of Game of Thrones, a lot of them are drone shots in the movie. Of course, aerial photography has existed for a very long time now, but drone photography happens to be fairly cheaper and in a way safer also than aerial photography from a manned aircraft. So there are this particular drone, I think, is currently the most expensive cinematography drone in the world. So yeah. Now, what do you do with all this information? You basically process the video or the image as it is. And this chain actually looks like this, from the sensor to the payload processor, which is on board, which I told you about how it converts the sensor information to electrical information. And then from there to the main computer that's on board the aircraft, where the camera data is put into a form that can be transmitted to the ground station where the pilot is seated. We've discussed this before during NACDeC webinars. Unmanned aerial vehicles or UAVs are usually not entirely unmanned. They're actually, they have a pilot on the ground who's also making sense of this information. So the mission computer has to put the data in a particular way that that the data can be sent. It's like a protocol. It's called a protocol. And from there, the data link or the communication link between the UAV and the ground station takes over and transmits this data back. Acha, you may also want to encrypt this information, especially if it is some kind of sensitive area that you're viewing. Then you may want to encrypt it so that you don't get intercepted, so that someone else doesn't get your information. So there may be encryption also on the way, and data link. And from the data link, of course, there's an airborne transmitter and there's a ground receiver. So this data is sent in packets. So it's sent one packet from up, the guy on the ground catches it, one packet from up, and the next packet is caught. So this is the way data flows. And it also, again, it requires, I'll come to that, it requires certain ways in which you can calculate how to send this data. And then, of course, it's post-processed on the ground station. This is not always the case with data flow. Sometimes there is onboard processing itself. All the data may not be sent to the ground. Maybe data is just collected and then you download it when you come back to the ground. So this is also possible because camera and video files tend to be very large. So you retrieve the aircraft back after landing and then you take the SD card off it and then you collect your data on the ground. So there are different ways to do it. It depends on how much the data is, what is the quality, what is the sensitivity of this data, etc. So there are various standard formats in which videos are processed. I won't get into this. Yeah, so this is what I was talking about. So there is something about how to send this video back to the ground, relaying this video back to the ground. Like I said, it's a large amount of information because you're shooting at 30 frames per second. Each frame is having that many 700,000, 1 million pixels. And now this 1 million pixels multiplied by 30, you're sending back to the ground, right? So it's a lot of information, frankly. And the amount of power that goes into this, because of the way the atmospheric losses take place, because of the way physics works in general, intensity of a signal changes with the square of the distance between the transmitter and the receiver. So as a result of this, you initially might have a very good margin, but as distance increases, as the square of the distance, your amount of data that can be transmitted reduces. So those who are from an electronics background might have seen this kind of a diagram before, which is basically the attenuation of a radio signal or of a data link signal with link range. On the x-axis, you see the link range, on the ground slant range, and on the y-axis, you see the margin or the strength of the signal, you can say, in a way. So the strength of the signal reduces parabolically as you increase with distance. So what are the different ways that are available to do this? You have satellite communication, you have radio frequency data links, and nowadays people are also doing this over 5G from very small UAVs like FPVs. So leaving the third one aside, because that's not relevant to us, for the Thar UAV problem statement, you have been asked to figure out a way to transmit this data back at the rate of, I think, 1 frame per second or something. So it's not a very high rate. So you may select either of the other two options, the SATCOM or the data link. It is a beyond visual line of sight. So usually the RF data link will not be working because first of all, the link distance is very large. So the amount of power that you'll have to put in to send data back is very large and does not fit in the weight category that we are talking about. So that is one thing. But if you are able to figure out a very good data link, then sure, like you can add that. But a SATCOM is what we have asked for. Now, satellite communications come at a cost. They are fairly expensive. So the bandwidth that you have, because of course SATCOMs are transmitting data over, like, if the satellite is thousands of kilometers away and you're sending it that far and then bringing it back. So it's an expensive affair. So that's why your problem statement allows you to send only 1 frame per second back for beyond visual line of sight communication. So there are certain types of SATCOM which can send this kind of limited amount of data. So to summarize everything all together now, this is the typical UAV payload stack. The stack consists of all of these things that we have seen. We have seen the daylight or the visible electro-optic spectrum. You've seen the medium and long range, long wave infrared thermal cameras, then the laser rangefinders, designators or illuminators, then the mechanical parts of it, like which is the pan tilt turret, the stabilization gimbal, and also a little bit about how this video is processed on board and analyzed. So what does it really look like in reality? Something like this. A typical camera of the weight class similar to what is on the Thar UAV looks like this. Now, if you can make out This camera has one axis, the horizontal axis. So this is the basically the tilt axis. And then you have a vertical axis, which is the pan axis. So this is how the UAV is mounted, is above this. This is mounted on the belly of the aircraft. So it can basically see the entire hemisphere below. Okay. And this particular camera has, you can see all these various apertures here. So you may have a daylight camera, which may look like this. You may have a thermal camera, which may look like this. And these are the kind of wavelengths that this works in. Inside this station are a lot of the other elements which we spoke about: the lens, the shutter. Sometimes these are also they are hermetically sealed compartments so that humidity can't get in and destroy the quality of your image, etc. So these are very, very specialized kinds of cameras which are used for surveillance in flight. And yeah, of course, this is, I think, a 1.3 kg camera. And the part that becomes heavier in these kind of cameras is actually the glass lenses and the optics and also the onboard processing that goes into it. So everything starts getting heavier the more you increase your specifications of what you want. I think you already have received specifications of one camera for the Thar UAV application, so I won't get into that. This is a different one, but similar weight class. Coming to that, for the NACDeC problem statement, if you haven't already, you need to take care of all of these aspects when you're designing your UAV for the camera that was given to you. You need to take care of the drag effect because, as you can see, it's got a particular turret shape and a stabilizer shape. So that particular the drag it's basically protuberance drag that gets added. Of course, all of you have cleared, many of you have cleared the IDR phase. So you have already taken into account the weight of the camera. Then how much power needs to be drawn by this camera? I'm not sure. I think this was provided in the data, but you need to ensure. I don't know about the NACDeC problem statement, but in general for UAVs, you have to be careful that you're carrying enough power to run this camera, to be able to run it. So, for example, it may run at a voltage of 24 volts and might draw 2 kilowatt, for example. So you need to ensure that for the duration of your flight, which is, let's say, 10 hours, your 2 kilowatt can be consistently provided so that the mission can be completed. And of course, finally, the mission profile is also affected by the camera. For example, there are certain altitudes which cameras work at best. And because of the way the winds are, because of the way stabilization happens at those altitudes, also because of the Johnson's criteria that we spoke about, where you need to be able to detect, identify, recognize a human or a vehicle or whatever it is that you want to identify on the ground or in the air. So the mission profile and the kind of altitude, speed, and maneuvering profile, like waypoint profile that you build, depends on the kind of camera that you have. In the case of Thar UAV, you don't have to worry about it so much. What's been given to you is already, it takes care of all of this. So, but when you do come out into the real world and when you're working in a company that's designing UAVs, you are going to have to start thinking about this. So that's the impact on aircraft design of cameras. I think I've covered everything now for electro-optic payloads. And with that, I will end this presentation and I am now open for questions. Utkarsh has, lead Utkarsh has raised their hand. You can unmute yourself and speak.
Hello, good evening, ma'am.
Good evening.
Yes, ma'am. Can we, for all the teams, can you give us the power required for the mission for this AOIR camera and the
Uh,
resolution?
so as of now, you don't have to worry about it. It has been taken care of. It's a very small part that's there
Because,
on it.
because, ma'am, we are for the battery sizing
Yeah.
area. We are assigning power for this flight computer servos and all, and only this AOIR system is remaining on that thing.
Okay.
So the sizing for the sizing issue, one These two things we had required, the resolution and power for the thing.
Okay, so we'll see what we can put out for you guys. In the meantime, what you should actually do is you already have some dimensions and weight that's given to you. The hint is that it's based on a real life camera. So go and look at what cameras are out there and approximate something for now. And we'll also share some data. If you email us, then we'll share this data with you.
No, moreover, I would like to butt in here. So thank you, Tanvi, for a wonderful presentation, as
Thank you.
always. It's great. The thing is, we are not here to answer specific queries regarding the NACDeC problem statement. Okay, if you have any query regarding the problem statement, you have a WhatsApp group, you have an email address, you ask there. The webinars are meant for general education and information, not for giving specific hints on the problem statement. So please refrain from asking questions which are related to your current problem statement.
Tanvi, you're muted.
Thank you for pointing that out. I was addressing the next question on the group, which is, does the speed of the aircraft affect the image quality in EOIR? The answer to this is yes, it does affect. It really depends on which EOIR has been selected. I didn't go into too much detail in this presentation because the time was limited. But there are certain things like if you ever, for example, if you take your camera and you try to zoom to its max extent, if you have like 10x zoom on your phone, just try to do it and then try to maintain whatever you're looking at within the phone's screen. You'll find that it's getting very difficult to do. So this is because the field of view of the camera has become very small and the field of view is hard to maintain. Now, actually, I have a video which shows how something can be kept, within the field of view of the camera. It's called image tracking. So let me just share quickly with you this video. Did you see how it zoomed out from the list? That's what I was talking about. And here is the part where image tracking comes in, which is actually really resolution at a range of 2.7 kilometers. So the aircraft is also moving and the camera is also doing its pan tilt at the same time. Can you imagine how hard that is? Yeah, so to answer your question, yes, definitely, it has an impact. If this question was about NACDeC, then you don't have to worry about it. Any more questions? There is a question. Can a stereo camera mounted on a surveillance UAV accurately identify and track objects from the air? If this question is about a stereo camera, now we didn't really discuss stereo in this talk. A stereo camera is basically like how humans view objects. We have two eyes and we have stereoscopic vision. What it means is there is a light signal from one eye and a light signal from another eye. Our eyes are able to detect the lag between these two or and interpolate how far something is by doing by depth. It's kind of a depth analysis, you can say. Humans are able to perceive depth because of the stereoscopic vision. So I think the answer is clear. I mean, what you see, the video that I showed you was also something very similar. So if a single camera can do it, then why not stereo, right? Okay. The next question is, how can we quantitatively co-optimize sensor modality, resolution, frame rate, and onboard compute under UAV weight, power, and bandwidth constraints to maximize end-to-end DRI performance via systems Can this person please unmute themselves and ask what they mean? This question is very complicated.
Yeah,
I'll need AI
actually,
to answer this.
Tanvi, the answer is it is very difficult to do all these things together at the same time. You
Yeah.
you cannot optimize for this and this and this and this and this together.
Actually, sir, actually, I want to bring out here that you don't optimize. It's kind of
Yeah, we
like
don't.
selection of engines. You have to go with what's available out there. Like you are an aircraft designer, you are not a camera designer, you are not a propulsion system designer, right? So you pick what's there on the market and you put it on your aircraft and see if it works. So
Correct.
yeah, and if you're a camera developer, if you're planning to become a camera developer, then yes, you have to do these things. But as an aircraft
So,
designer, you don't need to do this.
so in this particular project, in this problem statement solution, you don't need to worry
You don't need to worry about it.
optimization of all these things.
This is not part of the problem statement at all. There's no need to address this. It has been taken care of you at the camera selection stage already. So for as far as you are concerned, you don't need this right now. If you feel that you have some issues with fitting what you need into the weight, then you can see what standard avionics are used. There are a lot of architectures that are open and available. So you can check on that and see whether you can benchmark your thought process basically.
Okay, so we have reached 1 minute past 8 o'clock, which is actually our deadline. But if there are any burning questions or any queries, we would like to know from you. And you may ask questions not related to webinar, but also related to NACDeC 8 and NACDeC 9 planning, etc. If you have any questions. Submission is very near now.
When is the submission date, sir?
It's 15th June.
Okay. Oh, that's like 2 weeks from now.
So I would like to inform all the teams that do not expect any extension in the submission date, because we take a lot of time to go through the reports. We are also volunteers. We have another 1,000 things on our head. So don't expect any delay in the submission date. You have to submit by 15th of June. So put your efforts to finish it well in time. Okay, so if there are no more questions, then maybe I will. Oh, one person is requesting to be admitted. I've just admitted him. So last chance, guys, for asking questions to our speaker today.
So there's
How
one
important
question.
is FOM in then realistic design? So I'll answer this question. So see, you have been given FOM as a problem statement to be maximized, right? So you need to worry about FOM. How realistic it is none of actually your business, honestly. The user has told you that we want to maximize this FOM. So you can't argue with the user. Customer is king. So we will accept those designs which are having a higher FOM. Everything else remaining same. If FOM is better, we will prefer that design. But it should be feasible. It should not be some crazy design which is infeasible. So there is a question from leader of Udan team. Can we have a look at the chat window?
Can we integrate commercially available stereo cameras and other avionics into a surveillance UAV for real-time object detection and tracking? If this question is about Thar UAV, about NACDeC, then the answer is no, because you have been given a camera already. Please use the camera that's been given to you. In general, of course, this is what you end up doing.
See, you already have lots of things to do in your project. Why are you complicating your life by doing more things? Things which you have not asked. Why should you worry about them? You are taking part in the competition where there is a lot of tasks already there. Don't add your tasks because they will not get you any extra marks.
Yes. There are no extra marks for inventing a camera or for having a very stable camera design or something like this. The aspects of pan, tilt, gimbal, this, that, it's not part of the aircraft design process. Please don't spend your time in doing all these things. You have been
Yeah,
given
the webinar
your
was
mission
just to
profile.
educate you on these parameters. for your
Yeah.
general information, but we are not saying that please do all these things in the current problem statement, because that will go beyond the mandate of aircraft conceptual design. In aircraft design, we use payload as it is specified by the user. Okay, if that causes a problem because of weight, because of size, because of any other features, then you highlight that.
Yes.
But you don't end up reinventing the wheel by making a new camera or making a new payload. Okay, there is one more question apparently.
Can
Can
we
we
get
get feedback on IDR? Okay. Now, yes, you can. You can. So, general feedback on IDR is that our assessment was basically on go, no go. Okay. And the decision was based on our assessment on whether you have done enough work which can give us confidence that by mid-June you will be able to do a reasonable job and submit the report. Now, if we find that you are still struggling with very basics, or if we find that you have got all the concepts wrong, or if we find that you are just trying to use AI to create bulk and volume in the report, or if we find that your work is very frivolous, we have said, Baba, enough. Thank you very much. We don't want to continue with you, because we really value the time of our reviewers on the final reports that will be submitted by 15th of June. We want to go through them very much in detail. So that is the general feedback on IDRs. All the teams which are discontinued, primarily because of these reasons. Okay. Now, if some team has any specific query, well, we will be able to share the comments that the reviewers have given, but not. I mean, you know yourself. If you are a team who has submitted the report, you know what work you have done. But still, you are welcome to ask us specific questions, and we will give you specific answers. But we are not here to talk to every team and say this is what went wrong with your team. These are the general issues that we have seen being flagged by our reviewers. Too little work, incorrect formulation, wrong formulae used, wrong assumptions, no feel for the problem, simply using AI or simply using filling the report with literature survey. These kind of things have been flagged by our reviewers, and we have discontinued those teams. Okay, so if there are no more questions, then it's my duty to thank our speaker today for such a wonderful webinar. And recording will be available online, so those who could not watch can watch. Please use the NACDeC WhatsApp group and the email address for asking your queries, and we will be happy to answer them. With that, I wish you a very good evening, and see you sometime again. Please send a mail regarding what are the next topics for the webinars or topics for the next webinar that you would like us to touch, so that we can plan. And don't keep it too late. We need to do it in the month of June. So we need to know as soon as possible. Thank you so much and have a good evening.